On a previous video, one of my viewers commented that a mill isn't a mill unless it has a DRO. For the purposes of this intro, I'll agree. So let's get one installed. Welcome back to Cloud 42, I'm James. This is the PM-940 mill that I uncrated and set up in a previous video. I've done some basic checks with a dial indicator to make sure that it's trammed and that everything's square and running well. And now that that's done, the next order of business is to mount a DRO. Now, unfortunately, the mounting kit that came with my DRO doesn't fit this mill, so we're going to have to make a number of the parts we need to mount the scales and the reed heads. But that shouldn't be too big of a challenge because we have a milling machine. Unfortunately, this milling machine doesn't have a DRO yet, so there's going to be lots of counting turns of the hand cranks, but it shouldn't be too big of a problem. Let's take a look at what we need to make. I've built a mock-up of the PM-940 mill here in Fusion 360, and you can see there's some pieces missing, like the head, that just weren't necessary for the model I was putting together. I'm just looking to get the X, Y, and Z scales in place. I'll deal with the spindle scale later. For the Z-axis, we can take a look at that. That's pretty straightforward. I opted to just put the scale itself flat on the side of the column. I have seen this done with angles so that the scale is facing forward or backwards. I decided to go ahead and put it flat on the column. That way I can actually put the scale cover in place, and that will protect the scale from chips flying from the cutting point back. And I've got a sheet metal bracket here that will reach around that cover to the reed head and hold it in the right position. And then an aluminum plate here that will be attached to the Z slide. And it looks like I missed a joint on one of those screws, so it doesn't follow the assembly. So this is just a piece of aluminum, a flat bar I can mill out with the slots, and then there are jacking screws to adjust the height and angle off of this surface, slots to adjust fore and aft, and then that's just screwed to this sheet metal bracket. There's no adjustability at all in the sheet metal bracket because if I have to, I can bend it a little bit, but I should have enough adjustability here to get everything into the correct position. And then, of course, the scale has jacking screws and some slots to adjust its position so that it runs true up and down the column. I thought about I've seen photos with them attached in here. There's just not a lot of meat there to attach anything. You've also got this hole and this hole, which is where the gib locks are. So I've designed this to go inside underneath the handle of the gib lock, and the gib lock comes out and then has a big handle out here, and this shouldn't interfere with the use of that. So that's Z. Let's take a look at X. So I've opted to mount X on the back of the table, which is sort of the traditional location, but normally you would mount the slide on the back of the table and then have the reed head mounted with a bracket that attaches to the back of the saddle. This mill has an accordion style way cover, which I've shown here. That's what this big black box is. It's just an approximation in the right location, but it's in the way if I want to attach the reed head to the back of the saddle. I thought about spacing it out, but in the end just decided it would be simpler just to build a bridge over the top. Now, this could just be a bar that goes part way in and holds it, but I put the bridge all the way across because it's easy to attach and easy to align. And these are just a couple of pieces of aluminum angle, relieved here so it doesn't rub on the table, with a couple of slotted screw holes so that you have vertical and horizontal adjustment. I don't think an angle adjustment is going to be needed since these are both fully machined surfaces, but if they are, I can come and drill holes and put jacking screws in these little plates. So this is just a 1/2 inch square piece of aluminum bar, and the reed head is screwed directly into it. So then with the scale cover over the top, this should be just fine. And in fact, the vise is going to stick over the back a little bit, and this accordion has a minimum distance, and so this scale cover should come up and make contact with the column after the vise hits, or right about the same time that the accordion here is at its minimum dimension. So it should fit just fine, and this shouldn't lose me any of my Y travel. So for Y, this mill is a little bit tricky because the sides here are angled. Now I've seen people take the scale and just mount it flat on that angled side, and then the way cover ends up angling up, creating a little V in here where chips can collect. I really didn't want that, so I wanted to mount it vertically. Also, there's a vertical machine surface here that I can just mount a plate to drop down and come across. And I don't have anything funny to do in terms of angles on the reed head mount. So I designed up a couple little brackets here. These brackets are just a couple pieces of angle, but each one, these two are different, and each one requires two different setups. And it just seemed like a lot of work. So I came up with a plan B. And plan B is to take this angle, trim it down so it's the right length to match the angle on the side here, and then just tack weld it to a couple of little aluminum plates. Then I end up with one screw that goes into the mill base and two jacking screws on each end, and it just attaches easily with a couple of tack welds. I've got the equipment to do that. That should be quick and easy. That then gives me a vertical surface to attach the scale to, and then I can just drop a bracket right off the machined end of the saddle and bring another bracket over and screw that directly into the reed head. So then that whole assembly just slides in Y. Now I don't think angle adjustment here is going to be necessary because I can adjust and get the scale vertical. But if it is, I've got provisions to put 4 jacking screws in this bracket, and then with the slots that'll allow me to change the angle of this in every axis. And then there are slots down here to manage the in and out movement. And then of course the scale position can be moved up and down either with the slots in the scale and the jacking screws there, or with the slot in this bracket and the jacking screws there. So we've got lots of little parts to make. Where should we start? I think I would like to start up here on the Z-axis and start with this sheet metal bracket. I've had the heat on in the shop all day, so the CNC mill is warm, meaning the whey oil isn't going to be cold and sticky, so it should move freely. I'm going to take advantage of that and go ahead and mill this part first. Let's go out in the shop and get started. I have a piece of 5052 aluminum. This is about 1/8 of an inch thick. It's actually about 121 thou. And I have this super glued down with blue painter's tape. You've seen me use this technique before for milling out sheet metal parts. I need to locate this corner, and then we'll just mill out the bracket. Now, this is the first time I will be using the new fog buster on this mill, and I think I've got it tuned up. When I first powered it up, I had a little bit of a leak from one of the valves. It turned out there was a little hole in one of the O-rings. I replaced that, and it's running beautifully now. So let me grab the Heimer, and let's locate this corner. Okay, the first tool we need to run is a 1/8 inch end mill, and this is a 3-flute Lakeshore Carbide variable flute for aluminum. And this is going to be tool number 25. Okay, that went beautifully. And the other tool is tool 15, which is a 1/4 inch variable flute for aluminum Lakeshore Carbide end mill. And we're going to use this to contour out the sides of the bracket. Okay, I am super happy with the fog buster. Those two jets just cleared every single chip out. With the Noga Mini Cool that I was using before, I would still have a few chips left behind that were in the, especially when I was slotting this deep. In fact, I took this in 4 passes, and the last 2 were chattering a lot and recutting chips. But man, with the fog buster, with that dual nozzle, the chips are just gone. I have this running at about 15 PSI, and that is all it takes. Let me check the size of these holes. It's a 137 pin, that fits. 138 does not. This one's just a touch tighter. Yeah, that was about 136, 135 maybe. Yeah. Is there a chip in there? I think there's a chip in there. Yeah, there was a chip in there. Those are going to be tapped M4 by 0.7, so those are just slightly above what they should be, but they should be fine. Let me pry this off of here. Okay, it looks pretty good. I will go dress the edges of this off on a deburring wheel on the buffer. Okay, I'm going to just do a quick deburr the holes. That's that. Now we need to tap these, and then we need to bend it. I have a diagram of the flat pattern for this part, and this is 1-to-1. So we have the part and the pattern, and we have the bends marked. So I just need to take these dimensions and mark them on the part itself. Now the first one is at a height of 530. Let me first zero my height gauge here. That's good. First one is at 530. And I gotta think about how this is gonna go. That needs to be marked on this side. Put a little sharp'em on there. Put that up against a block and scribe the bend line. And you can see it, I almost missed. And then the other bend lines I'll need to go on the other side, and I can use the 1-to-1 drawing to figure out where I need to put the blue. And those are at 1.541. And at 3.690. Now let me put this down on the diagram here and just make sure against the drawing that it looks like it's in the right place. And it definitely doesn't. That's interesting. the one-to-one drawing here does not appear to match up. And it's the drawing that's wrong, because this says, I'm measuring it on the drawing here, I'm getting about 4.5 inches, and it's showing 4.711 on the drawing for that dimension. So that makes sense. I think we've got the lines all in the right place. Just the way the flat pattern generates, they don't appear to be adding the bend allowance. So, okay, hang on just a second here. I'm getting confused because the part I have in my hand doesn't exactly match the drawing, and I didn't realize until later that I, for some reason, had Adobe Acrobat set to print at 98% actual size. So my one-to-one drawing is just undersized. That's all that's happening here. But the confusion was enough to distract me so that I'm actually marking the lines on the wrong side of the part, and that will come back to haunt me later. Okay, so let's take this over and bend it. Before we get too excited, let's go ahead and tap these holes. It'll be easier to do while it's still flat. These are M4 by 0.7, got an M4 by 0.7 tap, and we'll just go ahead and run these in. Use a little A9 as lubricant. This is a spiral point tap, so the swarf goes out the bottom of the hole, so I don't have to worry about that with the tapping guide. And that's that. Okay. Grab my bending jaws here. And these are just magnetic jaws, magnetic bending brake jaws that go in the vise. And there's the bending tool. This one's very, very sharp. And we can just line these up and make the bends. I think I'm going to start with this short one. This just needs to come out to 90 degrees. That looks about right. And the other two need to do the same. I can kind of feel the line in there. And there's the part. Just like it looks in the CAD drawing. Now I'll get a square and check these edges and just try to finesse it a little bit. Yeah, so that's a little bit overbent. And that's the part. I'll take it over to the buffing wheel and take some of these marks off, and I think we should be good to go. And there we go. That part is done. Now, this is a very nice part that we've just made here, but since I marked the lines on the wrong side of the sheet metal, this is actually the mirror image of the part we actually need. Fortunately, I saw this old Tony video a couple of years ago where he was making a left-hand tap where he showed how to solve exactly this problem. Now, I'm not using the same video editing software that he was, but I believe mine has a similar function. And there we go. This part should now fit the mill, and we're good to go. There are a lot of parts that need to be milled, and we could CNC a lot of them, but I bought a manual mill because I wanted to turn the hand cranks, so let's turn the hand cranks. I took the vise back off of the mill. I never actually had it bolted down solidly yet anyway, because there are a number of parts that are large. like these scale covers that need to be cut down to size, and that's easiest to do on the table without the vise mounted. So let's start with those. This is the scale for the x-axis, and of course, since the scale itself, or this is the cover for the scale for the x-axis, since the scale itself has to be longer than the travel of the mill, this is the one part that's going to be too large to actually just mill end to end. So we'll have to do it in a couple of setups. So let me just go ahead and set it up here for the first cut and get it clamped down on the table. Okay, that's nice and solid. Now the only issue with this part is that it's just too wide. I need to keep this dimension the same, and then this outside dimension needs to be cut down, and it needs to be cut down to 30 millimeters. So let's see how tall it is right now. And yes, I will be switching back and forth with different kinds of units as we go through this, because different units were more convenient depending on what parts I was working with. So the height right now is 37.6. So I need to come down, touch this, and then drop 7.6 millimeters, and that'll be the correct height. Let me write that down. So I've got a slitting saw in here, and that's what we're going to use. This is Thurston. This is a very fine tooth pitch, high tooth count. We're going to bring that down, and I want to do a climb cut across this. And the reason for that is because of the shape of the saw and the way it interacts with the workpiece. Now, normally you would not want a climb cut on a manual mill in general, because it's possible for the backlash in the screw to be suddenly taken up by the cutter and allow it to pull itself into the work. But in this case, since we have a slitting saw, it's going to be rotating in this direction. If we're coming across the piece, engaging on this edge, if you get a little bit of extra bite in the sheet metal, it's going to try to flex it away from the cutter. And when it does that, it will then lighten the cut, so you get negative feedback and nothing bad will happen. If instead we were coming this way across the piece with the cutter exiting the work on that front edge, if the sheet metal flexed, it would flex into the cutter and take a bigger bite, which would then cause it to flex more, and you could get a catastrophic kind of a machine crash. We don't want that, so we're going to climb cut this. And the first thing I need to do is just spin this up and bring it down, and I'll just listen till I touch the top of this. Okay, so we're just barely touching, which means we need to drop another 7.6 millimeters, and I will do that with the DRO here. Okay. That's 7.6 millimeters. Let me get some cutting fluid to brush on the cutter, and let's make the cut. Now that we're far enough in, I'm going to put a clamp across the back side of this so that it won't make as much noise. And that is the end of travel. So now I need to reset some things here on the table and finish the cut. Okay, we're into a little bit of an issue in that the power feed on this machine sticks up above the table, so it's actually in the way, so I had to angle it, so I'll just drive it the rest of the way down here by hand. There's the 30 millimeters we needed, 30.19, close enough. Now the other ones, fortunately, will fit on the table, so I will just go ahead and slice all of those off, and I'll be back when they're done. Well, those turned out beautifully. This is the Y scale, and this is cut to 20 millimeters instead of 30. But after taking a nice swipe down it with the saw to slice it off, I ran it across the deburring wheel on the buffer, and man, you'd be hard pressed to even know that I cut that and that's not the factory anodized finish. I'm super happy with that. Now I did discover as I ran these other parts that you can run them way faster than I was running it. I was running at 345 RPM, bumped it up to 670, and then you can just run the crank through it just as fast as you can turn it. And it hits its resonance points where it gets really loud and squeaky, and then it passes it and it's fine. And if you just lay a finger on the off-cut side, it stops the vibration, and you can just crank that handle as fast as you can go and just wrap it right through the part, and it makes beautiful cuts. Now we need to do something very similar. We need to trim down one leg of this aluminum angle. Now this is 1 inch by 1 inch by 1/8 inch aluminum angle. It's not really 1 inch, it's like 1 inch 10 thousandths. And we need to cut one side of this down to 450 thousandths. We could use the saw, but I'm gonna do a setup down here, and I'm just gonna use an end mill because I'd like to see this thing make some chips. And I've got a 3/8 inch YG1 Alu Power end mill in here, and it's actually in the TTS tool holder from my CNC mill when I still had the R8 collets in it. And so I figured, give that a shot, see what it's like. And this again will be much easier to do on the table, so let me grab some clamps and put it down. We'll just run this one flat out as fast as the mill can go, and we'll take about half of it in the first pass and just see what it looks like. In fact, I'm going to back these clamps off slightly so that I don't accidentally mill them. Okay, let's see what we actually got. $757. You take another 307, and we'll just take that all in one swipe. That was beautiful. I love this mill. And that was not a challenging cut by any means, but if I had tried to run that cut on my little Grizzly, that would have been challenging. Would have made a lot more noise. This thing wasn't even complaining at all. 449.5. $450. I'll take it any day. And that is the finished product. And again, I'm just really tickled at the finish I got on that. Again, this mill is just so much more rigid than what I'm used to. I'm used to everything being a struggle and a trade-off between rigidity and speed and the size of the tool. And this is just a little 3/8 inch end mill, and it just plowed through this aluminum like it wasn't even there, making nice big chips. You hear that? They actually jingle because they're actually real chips. Okay, I'm pretty happy with that. The last thing that I have to do while we're here and have the table clean is I want to clamp down these angles, and I need to trim one side of these angles down to, drawing says 1.317 inches. So I'll just drop these under a couple of clamps here on the table. I got some grief in the comments on a previous video about why I spend so much time trying to make everything so accurate when it truly doesn't matter. And this is right. It doesn't matter. On a part like this, if this is off by 10 thousandths, if this is off by 100 thousandths, it probably won't matter that much. However, this is a hobby for me, and I'm out here working in the shop because I enjoy it. And I'm going to take the time. I'm not on a production schedule. I'm not trying to get something done. And I'm going to take the time to try to do the best job that I can for a couple reasons. One is because it makes me feel good about something that I've made. The other reason is because at some point, I'm going to have a project where it really is going to matter, and I will need to have the skills to hit the target precisely. So I'm going to try to hit my targets as closely as I can, even when I have something that's not critical, so that I can build the skill set that I need so that when a project comes along that is critical, I will have the ability to hit those numbers. So that's why I'm doing that. And if you want to rage in the comments, feel free. This should go right to size. If I were really, really concerned about this, I might take it in a couple of passes, but I'm not. I'm just going to go right to size. And just as a sanity check before I take it out of the setup, I am going to check it. My target was 1.317. Let's see what we actually hit. And we're at 1.319. So that is totally fine. I don't have an issue with that. Let's just check in to make sure there's not a burr that's affecting that measurement. Nope, 1.319. And the surface finish I got on the tops of those is beautiful. I'm actually really impressed with this little cutter. It's not really intended to be run that hard. It's not intended to be run dry like that, but it ran like a champ. I got a little bit of aluminum just starting to stick to the flutes. That'll knock off easily, and if I make my next cut with some cutting fluid, that'll clean up beautifully. So let me run these over to the buffer and take the edges off with a diamond with the deburring wheel. Well, I gotta say, it's nice to actually make some chips with a new machine, and this thing is working like a champ. Now, none of those cuts that I took today are challenging for a machine like this at all. They would have been challenging for my little G0704. Would have had a lot of vibration with some of those 300 or 350 thou deep cuts in aluminum, and this thing didn't vibrate at all. Someday we'll do some steel work on it. I've got a couple of dovetail cutters from Randy Richards on the way, and those will be the test. If we can spin those through steel and make tool holders for the lathe, Then we'll know how rigid this thing really is. I think the next thing to do on the DRO project is get the vise mounted on there so that we can make the rest of the parts, and we'll continue working on that next time. If you enjoyed this video, please give me a thumbs up. Feel free to subscribe to the channel so you don't miss the rest of the project, and leave me a comment. I'd like to know what you think. If you put a DRO on one of your machines, did you have to make a lot of parts? Did the default kit work? Let us know down in the comments. Thank you for watching.